Hello and welcome to my physics lab presentation. The goal of the first lab was to observe the motion of an object moving at constant velocity, which means it is moving at the same speed in an interval of time without changing directions. For this lab, I chose to observe the motion of a chapstick rolling across the table. The overall experiment aimed to compare the observed prediction and computational model prediction for the position time graph of the object. For the observed prediction, I recorded the chapstick rolling across the table at 30 frames per second and inputted it into Tracker, where I manually calculated its position at every frame. The video was trimmed to after a few seconds after it started moving and a few seconds before it left the frame to account for acceleration and deceleration and make it more accurately depict constant velocity. From the tracker and with the points I made, which are shown by the little red diamonds, I got the calculations for initial position and initial velocity. Initial velocity was calculated by using the first 2 points measured from the tracker, but can be found by using any of the 2 points from the tracker since we are assuming constant velocity. In plotting my points for position, I based them off of the object moving in the negative x direction. However, if I were to flip the negative x and positive x directions, the object would be moving in the positive x direction, and the graph I will show later would be reflected across the x-axis. As for the computational model prediction, I used Glowscript and the starter code and inserted the initial conditions that were found from the observed predictions data and assigned them to their respective variables. The approximate mass was given by the object's label description. While there was some velocity in the y component from the observed prediction, it was ignored and not added to the computational model since we are really only looking at the motion in the x direction. Since we are observing constant velocity, the velocity update formula based off of Newton's second law has to have initial velocity equal to final velocity. For this to happen, the net force must be zero, since neither delta t or mass are zero. This also refers to Newton's first law, as it states that an object has constant velocity only if net force is zero. Knowing our velocity is constant, we plug it into the position update formula as average velocity, because it is the same as initial or final velocity. We use a while loop for the iteration of Newton's second law to accurately depict the object's motion over the same time interval used in the observed prediction. These are the graphs obtained from the data through the observed and computational model predictions. This shows both predictions on the same graph. As you may notice, they are not too far off and have similar slopes. The discrepancies between these predictions, however, could be accounted for by minor errors in the observation of the object's position. It was manually calculated by the naked eye, which is not the most reliable. The object was also not completely aligned with the camera and did not seem to move in a straight line, so we can guess that it was also moving in the y and or z axis. The computational model may also not have taken into account other information. It was assumed that the object was moving at constant velocity, but the net force may not have actually been zero and could have been slightly greater than zero. We are not able to know exactly how many pushes or pulls are acting on the object because we cannot isolate the system. Other forces may have been acting on it, such as friction, air resistance, wind, or if the table was even slightly slanted, gravitational force. Overall, however, the results show that the computational model can be used to predict an object's motion using Newton's second law. One has to take the results with a grain of salt, though, because it will have some discrepancies to real-world observations. Thank you.